three things I want to talk about today are flood basalts, the Deccan Traps, Siberian Traps, Columbia Gorge specifically, although there are many more around the world, and seafloor sediment and Pliocene, Pleistocene break in the fossil record. So Deccan Traps, this is an image of the Deccan Traps, and this is in India. Another picture of it from satellite. And the word traps comes from the word steppe. And so you can kind of see how there's sort of a step-like pattern to all of these. And the reason is because this is layers of basalt. And it's one basalt flow on top of another. And then when it erodes down into these plateaus and platforms and stair steps. The time between each layer is estimated to be a few thousand years based on radiometric dating at the bottom and radiometric dating at the top. The radiometric dating is not precise enough to date, like if you were to get 50 individual layers and get dates for all of those layers, it wouldn't be precise enough to say, oh yeah, this one's definitely above this one or below that one, or like if they're too close to each other. But they can take the total thickness and figure it out roughly. Okay, original area coverage is estimated to be over 1.5 million square kilometers, so that's like half the size of the country of India. So imagine an eruption on the Earth's surface, that much lava, hundreds of meters of lava getting dumped out over an area half the size of India. And so there's a good reason that they think that this had to do with mass extinctions. Now when it comes, so a couple of things to think about though. Estimates are all over the place for soil formation. People think it takes a few tens to hundreds to thousands of years to form an inch of topsoil. And I'm sure, it depends how wet it is, depends what kind of rock it is. Basalt weathers pretty quickly, and this is all basalt. So we should get some topsoil in this area. This was not, if there's any precipitation, you're going to get some topsoil and erosion. But what's interesting is that we don't find any erosion or weathering at the contacts. So between all these layers, there's just no weathering or erosion. It's one flow of lava over top of another, even though there's supposed to be thousands of years of time in between each layer. This is the Siberian Traps. This is immense. Here's Moscow over here, and here is the other side of Siberia, way over here, and you can see how big this area is. Here's a picture of the Siberian Traps, and again you can see this kind of the stair stepping. They think it covered about 2 million years of total time. The area was about 7 million square kilometers, so significantly bigger than the Deccan Traps. And the thickness of the intrusives is about 250 meters, although it may have been much thicker, because if they need to do more research, they need to do more boreholes. And then this is the smallest and most recent. This is the Columbia River basalts, still substantial, and really beautiful area. This is where the Missoula flood came through and washed out this area, and you can see here again these layers of lava. More of the Columbia River basalt. And so this one has been studied very well, partly because it's not in Siberia, and and it's just accessible. It's in Washington State. It's a nice place to work.
So, how should I say level?
So the idea is that there were fissures that this lava flowed out of, and as the lava flowed out of the fissures, it formed these level sheets because it's liquid, and then as more and more lava flowed out, the ground actually subsides because it's losing mass down below, and so it forms this basin, and then the layers of lava just keep pouring out. And again with this one,
Well, how big is this area?
it is 210,000 square kilometers.
Wait, how can lava pour out and keep spreading that far? I mean, wouldn't it cool and harden and stop moving after just a matter of a couple hundred feet?
They've done the math on that. And what you so imagine pouring like glue out of a bottle, and if you pour it out really quickly, you squeeze a bunch of glue out, it'll form a puddle, right? But imagine pouring it out so slow that it dries on the way down.
Right.
It's gonna form a tangled mess of like just dry glue strand, right? Lava does the same thing. So if you get lava flowing very slowly, it will form. It'll form. Yeah, you can see it in Hawaii actually. Like you can see these pahoehoe flows that just kind of.
It's like a candle.
You get little tongues everywhere. Yeah. So this stuff actually filled a basin up to about 1.8 kilometers deep.
Whoa.
Yeah, this is. So you can imagine the effect on just the Earth's climate. If that. So I mentioned they did the math. This is some math on this particular flow. So the flow can travel at velocities of 1 to 8 meters per second, but it has to be laminar because if it's turbulent, it cools too quickly. And if you get it in less than a week, they think that if they place all of this in less than a week, they can get the whole flow out there and level. So the problem is, how do you get that many lava flows in place with no erosion or soil formation at the contacts? If there are thousands of years between these contacts. So we can see from the math, and this is well established in scientific literature, they've done the math on this, on how lava flows, and they know that that each individual flow has to be very quick. And they can look at a flow and calculate, okay, how did this actually happen?
These would have to be like back-to-back massive eruptions.
Yeah. So it looks, like if you're just looking at the geology, it really looks like back-to-back massive eruptions. But when you take the radiometric dates from the bottom to the top, then it looks like, okay, we've got to somehow get thousands of years in between each of these layers. But you can't see the thousands of years in the layers. That's an extrapolation based on these dates that they're getting. This is only one slide. This one is wild. It makes a lot of, like, if you tell this to a geologist, it's like, wait, what? And if you tell it to somebody else, like, okay. But 90 to 95% of seafloor sediment is Miocene Pliocene.
Okay.
Yeah, right? Yeah. Okay, so the seafloor, so Pangaea, the radiometric date for the breakup of Pangaea is about 200 million years ago. And so we should see sedimentation across the whole span of 200 million up to present, right?
Right.
90 to 95% is Miocene Pliocene. That is 23 to about 2.6 million years ago. So why in the world do we have the vast bulk of seafloor sedimentation happening between 2.6 and 23 million years ago? So I would say that this is something that is very bizarre from a conventional perspective, but makes a good deal of sense from the perspective of Pangea breaks up catastrophically. There's water everywhere, and then kind of at the end of this catastrophe, there's a lot of sediment flowing off of the continents back into the ocean, and so that would tell us when kind of the tail end of this catastrophe happened. Okay, the last little bit for today is the Pliocene break in the fossil record. So this is another one where a geologist might say, okay, that's really bizarre, and someone else is like, okay, but there was so Pliocene is way up at the top. Remember, Miocene, Pliocene is where the seafloor sedimentation happened. So Pliocene is about 2.6 million years ago or so, back down to that, and then everything below that point is buried in waterborne sediment. All of the fossils below that. Doesn't matter if it's a bat, a tree, a horse. It's all buried, it's all buried in water. Everything above that line is buried in a natural trap. Tar ice caves. So there's some huge shift in the way fossils were buried and preserved at that break in Earth's history. So this is a horse from Green River. This is Eocene, and we've got a replica of that over here. It's not very big. It's like.
Are those fish?
Yeah. So these are.
1, 2, 3. I see.
Yeah. So notice it's a 3-toed horse, but if you look at the skull of the horse, you can see it's a horse. Like, it's definitely a horse. Yeah. Yeah. And it was taking a bath with bats and palm trees also. Yeah. If you see the bat fossil, it's amazing. It's But yeah, terrestrial animals, they're all in water at this point. And then, later on, of course, we get like tar pit fossils and ice fossils, things preserved in caves and ice. And this is from the Tar Pits Museum.
Is that the sequence? Water, tar,
No. So it's just one. It's just one division. Everything below that is buried in water, like sediment, carried by water, and then everything above that is natural trap.
Well,
I wanted to add the 3 things that I just said to the list of other stuff that we've talked about previously. So I would say that independent arguments for a young Earth, and what I mean by independent is this argument does not rely on any other argument to be an argument in itself. And I'll give an example. Like, I heard somebody that was debating something that I had said was using magnetic reversals in the Earth's geologic record as evidence for old age. And I would say that's not an independent argument because those magnetic reversals are dated with radiometric dating. So it's anyway, that, like, for example, so flood basalts, coastal erosion rates, basinal erosion rates, and mountain range erosion rates, I would say that's kind of the same argument. Paraconformities, scarce bioturbation in ancient sediments, biomolecules and fossils, and carbon in the fossil record. Sorry, I meant carbon-14. Radioactive carbon in the fossil record. And then independent arguments for a biblical flood would actually be the seafloor sediment, the Pliocene Pleistocene break in the fossil record, where you have a major catastrophe that buries everything in water, and then after that, things get buried in natural traps. Vast catastrophic ancient deposits. So we can look at these layers in the fossil record, and you can see like the Tapete sandstone, the Cambrian sandstone at the base of the Grand Canyon. It has boulders the size of cars in it, and it covers a vast portion of the continent. just as an example. And then paleocurrents and taphonomy. Independent arguments for deep time. I wanted to include that just to be fair. Slow plate tectonic movement, but but it has been demonstrated by John Baumgartner that catastrophic plate tectonics are theoretically possible. We have heat transfer from large bodies of magma. This is a problem. We don't really know how to address this in a young Earth context. But I would add that there's an equal and opposite problem at the core mantle boundary where you have these huge masses of cold material that's sitting down on the core mantle boundary. And it makes perfect sense if they are the subducted plates, if they're the Earth's crust that was subducted during the flood.
At some point.
Well,
Recently.
Yeah,
recently, yeah.
Otherwise, it would have equal.
But the temperature would have equalized if it had been there for hundreds of millions of years. And then long half-life radioactive isotopes is another solid argument for deep time. But again, we have these short half-life isotopes that contradict it.